So take a quick look at the lower bounds, and I'm not going to spend too much time on the review, but just to show you the slides that we looked at. And we had this algorithm that any comparison sort requires a minimum of n log n comparisons. That gives you the complexity in the worst case. And we said that, perhaps I didn't explicitly say this in the last lecture, is that the height of the decision tree model will differ depending on the algorithm that you have. So, for example, in algorithms which have complexity of n log n, the height would be n log n. But for algorithms, and I think you've seen that in some, perhaps not exactly in this course, but in an earlier course, maybe in COMP 210, insertion sort, you should know that that has complexity, the worst complexity of theta of n squared. So depending on whether you're applying the decision tree model to a merge sort, or for example, insertion sort, then the height of the tree would differ. Okay, and the height of the tree, the maximum height, would give you the complexity. And then we started speaking about non-comparison based sorts, and we started looking at counting sort, and we made a big assumption here that we assumed that the range of the numbers to be sorted is up to a number k. Okay, so you have n numbers, but the range is maximum of k. And so if you used this particular assumption, then we went through counting sort, and I'm not going to go through that again. This is some of the examples from the book as well. And we saw that the complexity of counting sort was dependent on not only on n, but also on k, which was the range. So k, of course, can be extremely large, but generally counting sort is applied in those scenarios where k is of the order of n. Okay, so if a is of the same order of n, then the time complexity comes down to order of big O of n. Okay, it does have an extremely important property, which is that it is stable, right? So if you have two numbers being sorted and they're both equal, then the original place will be kept in this algorithm, which is not true for a lot of other algorithms. We saw that the amount of memory is not so good in the sense that it is not in place. So there is some additional memory being used, and so the space complexity also depends on k. And then we started looking at how can we apply this? How can we use counting sort for other algorithms? And so we started by taking a look at Radix sort, and this was right towards the end of the last lecture. So it utilizes a stable linear sorting algorithm, right? So let's make the following assumption that we have the following numbers. We have n numbers, okay? Numbers, and we need to sort them, okay? And now we want to utilize the concept that we earlier learned, which is counting sort. So any thoughts on how one could use counting sort, where we're making an assumption that the range of those numbers, k, is limited, okay? So how could we break up this particular problem, which at the face of it doesn't seem to indicate that k, the range, is order of n, right? So if you looked at these set of numbers, the first number is 726 and then 839, and this is 3 digits long. So what is the range of k? What's the maximum k that one can expect over here? Just to make sure you guys are awake. What's the maximum number for 3-digit decimal number? 999, and that clearly is extremely large, is nowhere close to, let's say in this example, 7. So you have a relatively small number of digits, of numbers, and now we want to convert this into something that utilizes counting sort. And counting sort is based on the fact that k is of the same order as n, okay? So how could we convert this problem into one in which k is now relatively small? And the term radix should sort of give you a hint, because radix means base, Okay, so for example, if you talk about uh, base 10 numbers, the radix is 10. If you talk about hexadecimal numbers, then the radix is 16, and so on. Now, binary numbers, the radix is 2. Okay. So any thoughts? How could we convert this problem into one that utilizes counting sort, where we limit the value of k? Yes, gentleman over here in the front. Okay. So what we could do, as being suggested, is that we could run it on each one of those digits. So if it's 3 digits, then what you could do is, and then the next question is, do you want to start off with the most significant digit or the least significant digit? So MSD and LSD, right? LSD here stands for the significant digit, not something else, right? So would you prefer to sort on MSD or LSD? LSD, why is that? Well, maybe you have the right answer, but let's understand the reasoning. Why would you not? And what could be perhaps the pros and cons of sorting on the MSD versus the LSD? And if I remember correctly, just before we ended the last lecture, I asked this question, and some of you suggested MSD. Okay, so whoever said that, can you think back? Why did you suggest MSD? And can I get your name? Sorry. Isaac. So would people agree with Isaac in the sense that he doesn't have an answer, but not quite sure why? So can somebody give a reasoning either way? MSD versus LSD, where would you want to start? So the idea is, yes, we want to use counting sort, and we've limited the range to k. K being, in the case of decimal numbers, is now going from 0 to 9, which is good. Yes. Yeah, I'm sorry. I was trying to point out the gentleman is the green sweatshirt. Yeah, sorry. I'll get back to you. Okay, maybe I pointed wrong. Yeah. Why? Right, right. So it's sort of like indicating that if you sorted the least significant digit, and then you sort the second most least significant digit, then the least significant digit is already sorted. And so one would think that, that you wouldn't have to do any more operations in sorting the lower order numbers. So the gentleman back who started answering. Yeah, if you had, yeah. Okay, so you've got some interesting thoughts. So you're favoring for the MSD, and we have a couple of people favoring the LSD. But can I get your name again? Logan. So Logan's suggestion is that if you use the MSD, then in a sense we know that if it's the number 726 and we're comparing with 839, then the numbers 700 are clearly going to be smaller, right? And so we've essentially sort of using a bucket sort kind of mechanism where we're putting 700 in the 726 in the 700 bucket and 839 in the 800 bucket. And so we've got, some control of the problem, that at least we've got the most significant digit sorted out. And then we can apply a sorting algorithm on within that particular bucket. Okay, so both of those suggestions are pretty good, right? But the earlier suggestion was that you could start with the least significant digit and then work upwards, and then you wouldn't have to sort anymore. Okay, so there's a difference here. In Logan's suggestion, you would still have a whole bunch of numbers to sort, right? But can I get your name? Christian? Nishan. So Nishan's suggestion is that if you start with the least significant digit, then if you sorted that and then you go to the second most least significant digit, then one of the advantages could be that you don't have to sort any further, at least on those two significant digits. Okay, so you can see there's some pros and cons, and while there are pros and cons on both sides, it's not like one of the technique is better than the other. All right, but simply because we're coming in from the counting sort background, and if you use the most significant digit, it turns out you can't really use counting sort. Okay, so and since we're trying to utilize counting sort, so I'm going to go with the least significant digit. Okay, and maybe when we have time, we'll go and look at Radix sort with MSD as well. Okay, so but right now we're just going to use LSD. All right, and so here's what we're going to do. This is it's a fairly simple algorithm, almost trivial algorithm. All right, so we start with the least significant digit. All right, we set I to be 1. Okay, so this is I is now equal to 1. We sort on these numbers, and we get the following. Okay, so after we sorted on the LSD, you get 0 over here, and so 0 goes up there, right? 9 goes down here. You have this 9 and this 9, and then you've got a couple of 7s. These 7s come together. The 0 goes up. 5, 6. So now you've sorted on the least significant digit. And now it's utilizing counting sort. Okay, that's our assumption. So we're going to use a stable sorting algorithm to sort these, and we're using counting sort. Okay, so if you're using counting sort, because it's stable, it ensures that if you have two numbers, 657 and 457, and 7 is common to both of them, then 657, because it was occurring before 457 in the original series, then it's going to retain that order. That's why it's called stable. All right. Similarly, 839 and 329, notice that these are not getting crossed over. Okay, that is going to be ensured by any stable algorithm, that these two are not going to cross over. Okay, so once you've done with the least significant digit, we go on and next sort on the remaining digits in sequential order. And so now we're going to sort on the middle digit. Okay, so we're going to sort over here. And so now what's going to happen is that these two 9s, well, we start with the numbers, the smallest number. So you have 2 over here, which is the smallest. There are a couple of 2s, so they both end up over here. Now, if you notice this, that you had 26 over here, and you have 29. Okay. Now, 26 and 29 are now 2 is the smallest middle digit. Okay, and it's going to appear at the top as compared to the 3s and the 5s, right? But the important thing is that because it's stable, 26 is guaranteed to appear before 29. Okay, and so what this is ensuring is that if you think about the last 2 digits, if you forget about the most significant digit for a minute, by having sorted this, just as Nishit had suggested, is that now the last 2 digits, these numbers are now sorted by the last 2 digits. Okay, so 26 and 29, similarly 3039, 55, 57, 57. So all of these are now sorted by the last 2 digits. Why is that? Once again, it's simply because you had earlier sorted by the least significant digit. And if these 2 are sorted and these 2 numbers are the same, then clearly 26 is going to be before 29. It's kind of almost obvious and trivial. All right. So it's a great algorithm. It works perfectly fine. You can see that as we go to the most significant digit, we now are sorting on the MSD, and now you have a couple of 3s, couple of 4s, and then 6, 7, and 8. And the fact that these two, the most significant digits, are the same, but you know that these two numbers are now already sorted, and these two are going to appear in the right order. And so when you are sorting with a stable algorithm, these two numbers will be in the right sorted order. Okay, so hopefully that's clear. And if you think about MSD, could one have used counting sort in any way? You can see how counting sort was used, and a linear sorting algorithm was used over here. But can you think of if you were doing this by MSD sorting, could one have utilized counting sort in any way? So to some extent, counting sort would be used, right? How would it have been used? It could partially still have been used if MSD had been used. Can somebody point that out? How would it have been applicable? Perhaps Logan, that's your suggested MSD, right? So do you see why? Do you see right in the initial portion that when you're sorting on MSD, would the counting sort still have been applicable? Or somebody else? So we're sorting, and this is an example of LSD, but let's say that we sorted on the MSD first, then, yes? Yeah, but it would have been doing it on the MSD, right? So you could have still done the sorting using counting sort on the MSD, but then you would have been stuck. All right, you couldn't have used that further on progressively on the lower order digits and still expect to get something useful. Okay, but perhaps you can work on that and see if you can come up with your own algorithm. Right, there's no shortage of algorithms when it comes to computer science students. So you can come up with your own algorithm and see maybe you can still continue to use counting sort using MSD. Okay. So next, let's take a look at the complexity. All right. So any thoughts on the complexity? So we're using counting sort. Do people remember what the complexity of counting sort was? We just saw that in the review. What is the complexity of counting sort? So we're initially applying counting sort over here on, let's say, the least significant digit over here. All right. How much time would that take? Yes. Yeah. O of n plus k, is that what you said? Yeah, okay. So we've got O of n plus k, or theta of n plus k over here, and that has to be now replicated, right? So how many times are we going to repeat that process? Yes. N times. So your thought is that it should be n times n plus k. That's looking like n squared. That doesn't look very good. Any other thoughts? Yes. D? Yeah. So if you assume that D is the number of digits, okay? So remember that we're doing for I is equal to 1 to D, okay? So you just, I think, got that confused. That should be D over here and not N, all right? So D times N plus K, you can clearly see that this portion is N plus K, and then you're repeating this D times, I is equal to 1 to D, so it's D times N plus K. Now, so this is the overall complexity. Does that look like linear sort? Can you make an argument either way, whether you would consider this as linear sort or not? Yes, Kyle. Right, right. Did you say D could be as small as 30 and 40? Okay, now, right now, we're not dealing with binary numbers, remember. We're dealing with decimal numbers. So, so D would not, even for a 32-bit number, D would be relatively small, right? It would be like 3 or 4, because 32 bits is sent to about 32, which is about 1,000, right? 4,000. 4,024, something like that. So now, if you're assuming that we're doing decimal numbers, then D will be even smaller, right? So it won't be as large as 30 or 40, because 30 or 40 implies that you have 10 to the power 40. 10 to the power 40 is extremely large number. So most numbers, would be in the range of 10 power, maybe 10, a billion or a trillion or something like that. So it might be under 10 or 20 if you're using decimal numbers. So you can almost, as Carla suggested, that D can be thought of as a constant. Okay, so for most range of numbers that one would typically have, D can be considered as a number small, maybe under 20. Okay, and if D is a constant, then in that case, this looks like a linear sorting algorithm, because now you have N, and again, you've already limited using decimal numbers K to be 0 to 9. Okay, so K is already 10. D is relatively small, let's say under 20. And so for most algorithms, this would be considered as a linear sort corresponding to theta of N, right? But it doesn't necessarily have to be the case. And one could come up with Radix sorting, which is not necessarily based on decimal numbers. So you could come with something more complex, in which you're using, let's say, instead of 2 bits or 3 bits or 4 bits to represent a single digit, okay? And that would make it a little bit more complex. The analysis would be similar, but I'm not going to spend time on that. And that's there in the book as well, all right? But the concept is fairly similar and can be extended. So this is the complexity for the examples that we've looked at. What about correctness? Do we really need to have an algorithm for figuring out the correctness, or it's almost trivial, right? It's kind of obvious. Nishit had an argument, and that actually suffices for most purposes, right? Because once you've sorted on the least significant digit, then if you next sort on the next least significant digits, it's kind of obvious that the two numbers would be sorted, because you've already sorted the lower order, right? And you could spend some time looking at this and understanding this. I'm not going to waste my time on this. This is almost, saying the obvious, that you could have formal proof of Radix sorts correctness as well. Okay, but you can read through this. So next thing, let's take a look at bucket sort. And if you sort of go back to, I think Logan made the suggestion that you sorted on MSD. And so you had all the numbers that say in the most significant digit put into one bucket, and so on. So bucket sort of is the general category of algorithms, which sort of what it does is it takes numbers and puts them into certain buckets, and then it sorts within the bucket, okay? As opposed to what we just did, which was starting with the least significant digit. All right, but the bucket sort algorithm is slightly specific, and it doesn't deal with all classes of numbers, but we're going to look at the classic bucket sort algorithm, in which there are certain assumptions made. So you're going to make the following assumption, that you have numbers which are uniformly distributed over 0 to 1, okay? Less than or equal to 0 and strictly less than 1, okay? So that's our assumption, that these are numbers between 0 and 1. And the second assumption is that they are uniformly distributed. Okay, so let's assume that they're being generated by using some random number generator, pseudo-random number generator, which probably should generate these numbers uniformly. All right. So that's our assumption. And we're going to generate, let's say, n of these numbers. In this example, you have n is equal to 10. And so if I were to say, well, if you had to sort these numbers, where would you start? Let's assume that you want to use bucket sort. You basically got the concept of bucket sort. How would you go about sort of similar to what we've already seen, but now the numbers are a little smaller. They're numbers less than 1. So how could you sort them, and how would you, how many buckets would you have? How would you go about doing this? Any thoughts on designing your own bucket sort? What would be the size of the bucket? That's one of the questions, right? So if you earlier we had the numbers, let's say these are the numbers. And so one of the possibilities would have been clearly that you use, because we're looking at decimal numbers going from 0 to 9, then you would naturally have 10 buckets, okay? How many buckets would you want to have in this particular case? Any thoughts? And you could come up with any number, and we could work with that. Doesn't have to be the best solution. Yeah. Number of digits. Well, not digits, because digits earlier we were referring to as the radix of that number. Okay. So you can sort of say is that would the number of the value of n, which is the count of the numbers. So is your suggestion that we make the number of buckets equal to the count n? Okay, so then essentially what you're saying is that we would, if you were dealing with decimal numbers, you would have 10 buckets. Or if you're dealing with hexadecimal numbers, you would have 16 buckets. Yeah. So that's one thought, and one could work with that. However, that's not what bucket sort is going to do. Okay. Bucket sort is going to say, well, instead of using a fixed number of buckets, we're actually going to use the number of buckets to be equal to n. So if you had 100 numbers, you're going to have 100 buckets. All right. Kind of seems a little wasteful in terms of space, because now what we're going to use is some auxiliary space. Clearly, because as you're going to take the original numbers and put it into buckets, those buckets need to have some array space. And so you're going to use a lot of additional space. So you immediately increase the utilize an amount of space which is theta of n, or at least order of n. Okay. So here is the actual algorithm. And the algorithm says that we're going to divide these numbers into n equal size buckets. Okay. Not equal to 10 or the base, but we're going to use a lot of space. Okay. And then we're going to start off by creating, in this particular case, it just so happens, this is the example from the book, maybe not the best example, but here n also happens to be 10. Okay, but that's not going to be necessarily the case. So you could have 20 numbers, you would have a bucket, which is the array B, is going to be size n. Okay. And then what we're going to do is we're going to start putting these numbers into these buckets. And the idea is very simple. So if it's 0.17, okay, we're simply going to convert that into a number 1, and we're going to put it in the first bucket. Okay. If it's 0.39, we're going to put it in the third bucket. Okay, simply going to take the decimal value over here, the most significant decimal value. However, it's not necessarily going to be limited to n. Okay, and here's the actual algorithm. Okay, so what we're going to do is we're going to start off by making B. We're going to initialize it as a new array. We're going to set it to be 0. Okay, make it empty. And then we're going to take n and we're going to multiply it by the value of AI. Okay, so you can imagine that in this particular case, it's fairly simple. We're taking 0.17, we're going to multiply it by 10, that becomes 1.7. And then we're going to take the floor of that decimal number, that becomes 1. and we're going to put it in the first bucket. But that doesn't necessarily have to be the case. If n, for example, was 20, then you would have 20 buckets, and it would be a little different. Okay? But this is a simple example. Once we've put these numbers into the corresponding buckets, there will clearly be some buckets which will have no numbers, and there'll be some buckets which will have more than one number, right? Simply because even though the numbers are uniformly sorted, uniformly distributed, it doesn't necessarily mean that you won't have some randomness. Okay, so you will have some randomness. For example, you see that 0.21, 0.23, and 0.26 all will fall into bucket number 2. Okay, and so then the next idea is that once you put them into these buckets, we're going to sort within the bucket. Okay, and in this example, well, not this example, but this is the official algorithm, they're actually using insertion sort. Now, for those of you who have forgotten insertion sort, let me just remind you that it's sort of like, you have a deck of cards, all right? You have a new card and you're putting it inside your existing hand. So you just compare the numbers and you place it inside, okay? It's a very simple algorithm, okay? And it's an in-place algorithm, so it doesn't take up a lot of space. But the worst case complexity, if you think back, was theta of n squared, okay? So worst case complexity is actually pretty bad. But it's good if you have small set of numbers, okay? So because the assumption here is that, so let me ask you, why do you think this algorithm is suggesting using insertion sort to sort these numbers based on what I just said? Why do you think that we're using, why not use merge sort or quick sort, one of those divide by conquer algorithms? Yes. Yeah, exactly. So because of the fact that we have the same number of buckets as the number of numbers, okay, and they're uniformly distributed, so hopefully the number of collisions, so to speak, will not be too many. And on average, strictly speaking, the number of numbers in each bucket is actually going to be 1 on average, all right? Simply because some of them will be 0 and others will have more than 1, okay? But on average, the expected number of numbers is going to be small, and so you can use something like insertion sort, which is good for small set of numbers, okay? But it is bad because its complexity, if you were sorting, let's say in this case, you had 3 numbers over here, the complexity would be order of 3 squared, okay? It would be order of 3 squared. And so the question is, what do you think would be the complexity of this algorithm? Okay, and once you've done this, then it's clearly very simple. You simply concatenate these lists, and here we use sort of using linked lists. Okay, you can see from the diagram that we're using linked lists to perform this. So if you look at this algorithm, the question is, what is your intuitive analysis of the complexity of this algorithm? Right, it does have a little bit of quirkiness, you might say, is that because it's using inside it an algorithm which has a complexity of order of n squared, where n would be referred to as the number of elements inside a particular bucket. Okay, so if it wasn't for line 7, let's just disregard this for a minute. Okay, what's the complexity of this algorithm? If we didn't have to sort within that bucket, what would be the complexity? Yeah, it would be linear, right? Simply because it's order of n, and all we've done is you used a large amount of space, and we've put these numbers in each one of those in that array. Okay. And so it's a great way of sorting. If you don't have a limitation of space, you could use an extremely large bucket. You don't even have to have n buckets. You could use n times 10 or 100 or 1,000. And that way you would almost be sure that there would be no collisions. Okay, but in this case, we're not using a very large size of the bucket. We're just making it equal to n. So in that case, it's clearly linear. However, what about this? How does this particular line statement, change that. And what do you think is your intuition? What's your intuition saying? What would be the overall complexity of this algorithm? Will it still be linear, or will it become worse? Simply because there's an order of n squared inside it. Yes. Okay. So what you're saying is, instead of looking at the worst case analysis, which may be actually order of n squared, perhaps. All right. What you're suggesting is that let's look at the expected, right? Because it's sort of like there's some randomness involved over here. So if we, instead of looking at the worst case, we look at the average. Can I get your name? All right. Levi. So Levi's suggestion is that if you look at the average case, instead of the worst case, his intuition is that it's going to be, it seems to be linear. Okay, that's simply because the number of collisions, so to speak, would not be very high, because given that it's uniformly distributed and you have so many buckets. Okay, so that's a good intuitive response. But would you say, you've sort of implied it, but would you say what would be the worst case situation? What's the worst case complexity? n squared, right? And that would happen simply because if all of those numbers happen to be in the same bucket, extremely rare, but that's still possible because those are random numbers. So if all of those numbers happen to be in this particular bucket, then you'd have an extremely long linked list, and then you're sorting a linked list, and that would be order of n squared, because you're using insertion sort instead of merge sort or quick sort. Okay. So your intuition is exactly on the dot. This is essentially what we're saying, is that we expect that each bucket to have a few elements, and so on average, if you have one element per bucket, then you can simply say that it's taking order of 1 to sort each bucket, because it's a constant number of numbers. Okay, and so order of big O of n. Okay, so that is our intuition. But unfortunately, in this course, we don't always go just by intuition. We have to do a rigorous analysis. All right, that's the nature of this course. So let's do the rigorous analysis. And this will take a few minutes. It is a little tricky, but once you see it, hopefully it's not so bad. And it's got mostly a lot of math in it. All right, and if you can go through the math, it's not that difficult. It does require some of the probability, that we studied earlier in this course, and that that does come in handy. And of course, is going to utilize some of the concepts that we studied earlier as well. So let's start it off. So we're going to say, well, let n sub I be the number of elements placed in bucket I. Okay, n sub I is now the number of elements placed in bucket I. And so if we're assuming that, and we're given that insertion sort runs in quadratic time, so you can say that the time complexity is theta of n. Why? Because we're simply going through, if it wasn't for the quadratic portion, it would simply be theta of n. Plus the time to do the sorting. Okay, and the time to do the sorting will simply be for each one of those buckets we need to do a sort. Okay, so we're going from bucket 0 to bucket number n-1, and each one of those is going to take order of n sub I squared, just as we just agreed. Okay, because n sub I is the length of each one of those buckets. And so next, what we're going to do is, now we're going to do, instead of a worst case analysis, we're going to do an average or expected analysis. Okay, we're going to take expectations on both sides. Expectations, as you know, are linear. Expectation of x times the probability of x, so it's linear in x. So you can always apply linearity. So you can take these brackets out. You can say expected value of theta of n is still theta of n. Expected value of this, you've got a summation over here, so you can pull the expected inside that summation. Okay, and so you essentially got the following equation, which we need to sort, figure out. Okay, is that humming sound coming from this thing? It's kind of annoying. Is that some coming from somewhere else? Let me see if turning this off helps. It doesn't help. Sorry. Sorry. It's construction all the way outside. Okay, it's nothing to do with electronics once. Okay. So, so we have to solve the following equation. All right. And how do we solve it? Well, now it becomes a little tricky because we need to get the expected value of, and this is referred to as, what is this? If n is a random variable, what is expected value of n squared called in probability theory? Does anybody remember the word moments? Expected x is the first moment. Expected n squared is the second moment. Okay, if you haven't studied that, that's a useful term to know. That's simply the second moment of n sub I. Okay, and essentially what we're saying is that the second moment or expected value of n squared is essentially a constant. Okay, but it varies with n, but inversely proportional to n. Okay, so as n becomes larger and larger, the expected value of n squared is the order of complexity is essentially a constant. Okay, it does depend on n sub I, but it depends on it inversely. Okay, so that's a nice property to have, but we need to prove that. So let's take a quick look at the proof, and then we're going to use our favorite indicator random variables. Okay, you thought it would never come up, but yes, it does come in. So let's define the indicator random variable xij to be the event that a sub j falls in bucket I. Okay, so here's an example. So if you look at bucket 1, all right, so bucket 1 essentially says that it is a sum of two indicator random variables. These correspond to A8, okay? That has a value which was going to fall into bucket 1, and bucket and A2, which has a value of 0.17. So these are the two numbers which will eventually fall into bucket 1. Okay, so A8 and A2 will fall into bucket 1, and that's how you're defining xij. Okay, so that's the indicator random variables, and so the probability that a sub j falls in bucket I is simply 1 upon n. Why is that? Because these are uniformly distributed. So what is the probability that the this number A8, okay, is going to fall into a particular bucket? It's simply uniformly distributed. So it's going to be 1 upon n. Okay, that hopefully is not hard to digest. So now what we're saying is that n sub I can simply be represented by the sum of all these indicator random variables, which is exactly what I've shown over here. Okay, so n1 would be this, and similarly you could construct different values of n sub I. Okay, so we've defined what n sub I is, and so from here we can calculate the expected value of n sub I squared. Okay, any thoughts on that? Would that be trivial, non-trivial? How would we calculate the expected value of n sub I squared once we have this equation? Any thoughts? How would we calculate the expected value of n1 squared, given that n1 is given by the following expression? Let's make it simple. How would you do that? Is that completely trivial? Will the law of will linearity apply in this case? How would you calculate expected value of n1 squared? And I've given you a simple example, right? How would you do that? So n1 comprises of two random variables, and you want the square of the expected value of the square of that. Yes. All right, so you've got x1 squared, the expected value of x1 18 squared, expected value of x21 squared. Is that it? Is that what you're saying? Right. So the expectation is still there. So yeah. So I'm going to be multiplying it when I'm doing when I'm going to calculate the expected value. I'm going to say what is the probability of x18 being equal to a particular value. So we're going to do the expectations initially. But let's just keep the expectation outside for right now, and let's just work with the actual number. Okay. So if the expectation is still outside, would these two be the only two terms inside? We're taking the sum of two numbers and we're squaring them. Back to basic algebra. Is this it? It's kind of obvious, but I just want you guys to think. So is this what we're going to have? Is this going to be right? We're taking the square. We have two random variables. We're adding them together and we're squaring them. Okay? Yes. Yeah. Right. That's what I was looking for. So you'd actually have another term, which is going to be, a plus b, the whole squared is a squared plus b squared times 2a plus 2ab, right? So you have this other term as well, 2x18. Sometimes I ask you the obvious questions just so that you guys are awake. All right. So that's how it's going to be. You've got these. Now remember, these are random numbers. Okay. So how would I calculate the let's say if I'm looking at this particular term, how would I calculate the expected value of this particular term? Expected value of, let's say, x18 times x21. Okay. Now it's a product of two random numbers. I need to calculate the probability of two random numbers multiplied by each other. Does this remind you of anything that we covered in the probability section? And can we use some of that to figure this out? How would you calculate this? So when you have random numbers multiplied with each other, what do you start thinking about when you're taking expectations? Remember, we had this equation, probability of A and B, right, is equal to something, something, and becomes simple in some scenarios. It's not that simple in other scenarios. In what scenario does the joint probability of A and B become simple? When they're independent. And is that true over here? Is x18 and x21 independent? Why is that? So yeah, in a sense, each one of these numbers has been independently generated. Let's say it's been generated by a random number generator. And that's one of the assumptions we sort of had, but I didn't state it explicitly, but the assumption is that these numbers are not correlated, okay? These numbers are not your grades, let's say, for example, in this part, because there would be a strong correlation, right? And they would certainly not be uniformly distributed. Hopefully not, all right? More A's, B's than F's. So, so the assumption is that these are independent, and if it's independent, then what does it become equal to? If two random numbers are independent, yeah. Perfect. So now what you can do is you can separate these out simply because they are independent. Yes. Yes, because that's how we're defining it. So if you look at this, it's xij, which is the probability that A sub j falls in bucket I. Okay, so when you say x18 it's the event that A8 falls in bucket 1, not 18. Okay, so that's how they just defined it that way. You could define it the other way around, but that's how they're defining it. Okay. So so the answer that I got was that you can, if they're independent, if you have the assumption that each one of those indicator random variables are independent, which means that the numbers that you had were not correlated. There was no correlation between them, that they're independently being generated. Then the expectation, the joint expectation, is equal to the product of the individual expectations. And that goes way back to the probability of two random numbers being, two events being independent. Okay. So we've got portion of this solved. Okay. And so what would be the expected value of each one of these? So what would be the expected value of, let's say, x18? How would you calculate that? Expected value of x18 is equal to what? Now remember, this is an indicator random variable. Yes. Okay, so first of all, we have to go through the motion, which says basically that it's an indicator random variable. You have to take the values 0, or it'll have a 0 value or a 1 value. So you have to take 0. The probability, what's the probability that it has a value of 0? Well, so it's going to be well, let's just show it over here. Okay, it comes in a little bit later, but just hold on to this thought, and we'll come back to this, because every time you're taking the expectation of any random variable, you have to do a summation over all the possibilities times the probability of that event. Okay, so it's an indicator random variable which has either value of 0 or 1. Okay, so we'll take 0 times the probability that it's going to be 0 times 1 times the probability it's going to be 1. Because we have to go through that, and it might come out to be 1 upon n, but let's just hold on to that. Okay. So if we sort of seem to be making the problem into smaller problems, which are easy to handle. We've got this portion solved. We still haven't figured this one out. Okay, but let's do that as we go forward, because indicator random variables do have some nice properties. Okay. So let's take a look at the first term first. Okay, so we're going to look at this x18, for example, squared. Okay, or the entire term. So we've already got this. So this is something that we already saw earlier. We have the product of these two. Now you might say, where is the 2 coming in? We had a 2 over here earlier. That is sort of embedded in this double summation. Okay, you should be able to figure that out. All right, but you can see that this is essentially the same as the previous equation. Okay, because there are some duplicates over here. J is going from 1 to n, k is also going from 1 to n, and j is not equal to k, which is essentially saying x18 times x21, 18, and these two numbers can't be the same because that's already taken care of over here. Okay. Okay, so this is the expression that we already had. Okay. Now let's take a look at what, and can I get your name? Sorry. Yeah, Abe. So Abe had suggestion about how to calculate different values. So let's see if Abe is right. And it seems like you are correct. That was for, well, this is for the square of the value. Okay, but essentially it should be the same. All right, because you're taking 0 squared, multiply the probability of that event happening, times 1 squared, times the probability of that event happening. Okay, because it's an indicator random variable. So it's 0 times something, I don't care what this is because this is 0, and it's 1 times the probability that a sub j bucket falls into bucket I, and that was, we had already seen that's 1 upon n. So it comes out as 1 upon n for the second moment. Okay. And for the first moments, you write as well. What Abe had suggested is that it's going to be 1 upon n. You can see that each one of them is going to be 1 upon n, and you could do something similar to this, but either way, it's kind of hopefully straightforward that it's going to be 1 upon n. Okay, so now we've got solutions to most of our problem, and we still haven't solved for all of it. Okay. So now the expected value of n sub I squared, which was coming in from here. Okay, so we simply plugged in these values over here. Okay, so we've plugged in 1 upon n over here and 1 upon n squared. Okay, and so 1 upon n over n times you've got an n multiplication because it's going from j is equal to 1 to n. And so these n's cancel out, and then you've got a double summation. N 1 upon n squared is a constant, and you've got a double summation, and that simply is n times n minus 1. Okay, and you've got a few cancellations over here, so it comes out as 1 plus n minus 1 upon n, and that can be seen to be 2 minus 1 upon n. Okay, so that was a long series of steps, but essentially this is what we've been able to show, that the expected value of the second moment is essentially a constant, okay, with some small value of n coming in. And so if you look at our original problem, which was trying to find the complexity of the time complexity, which was, we already knew was theta of n times this particular expression, which you want to solve for. And so if you now have a solution for the second moment, we plug that in over here. Okay, we're summing over 0 to n minus 1. And essentially you multiply that by n. And so you come up with order of n. Okay, so this cancels out and this becomes 2 times n, which is big O of n. So after all of that, we are back to where we started off. Our intuition has been now formally proven to be correct. Okay, so so essentially, if you think about the big picture, what we've been able to see is that because of the following term, the insertion sort, simply because the size of that is relatively small, it doesn't have a big impact. It does have some impact, which results in a 1 upon n factor. Okay, and that 1 upon n factor gets neglected when you're looking at the order of complexity, and so this whole thing comes out to be theta of n. All right. So what have we been able to achieve? Can somebody fill in the question marks over here? We show that the counting sort, the worst case is theta n plus k. We are hopefully sure that this the worst case is this. And I've put in some question marks because I want you guys to think whether it's the worst case or the average case that we're talking about. So just help me out over here. Can people fill out these question marks? So bucket sort, what did we get over here? Theta of n, is that the worst case or the average case? That is the average case. So that's theta of n. What was the worst case? Was n squared. So that was n squared. And what about the average case for counting sort and Radix sort? Do you think it's going to be different as compared to the worst case scenario? Now think back as to how the algorithm is operating. Is the average going to be different as compared to the worst case? So you'll have to think about it a little bit, but hopefully you should be able to convince yourself that this, even in the average case, you're still going to end up with these operations. Okay, so if you look at how we were doing those operations, so you still have to, regardless of how the numbers are, even if they're all sorted, okay, you would still have to go through the process. Okay, so you would still have to go through theta of n plus k to do the counting sort, and then you'd still have to multiply it by d times. Okay, so even the average case would unfortunately still be no better. Okay, so and the Radix sort is similar. So essentially, both of these, the average case and the worst case, are the same. And in bucket sort, the worst case is actually a lot worse, simply because there's the element of randomness in there. Okay, so that sort of ends our look at linear sorting algorithms. And now let me just spend a little bit of time going over. We're going to go back to chapter 6 of of Corman and look at one of these early algorithms that are left out. And as you hopefully are aware, heap sort is based on the data structure called heaps. Okay. Now, this is going to be sort of a test for how much you remember from hopefully 210. Okay. So let's take a look. It's obviously a comparison sort algorithm. It uses a data structure called heap. Okay. And it is nice because it does have, other properties, which is it can do priority queues. All right. So let's take a look at the following heap. Okay. So as a reminder, if you're using a max heap, okay, we're making sure that a max heap has the following property, that the top of the heap has a number which is greater than or equal to all the numbers on the left or the right. Okay. And it is also called a complete binary tree. All right. So if those of you don't recall what a complete binary tree is, it's essentially a binary tree in which all these levels are filled, except for perhaps the last level. And the last level, all the nodes are shifted to the left. Okay, that's what is a complete binary tree, as compared to non-complete binary trees, which could have holes in the middle as well. All right. So we could have an array representation. Okay, so I'm going over this a little fast because hopefully this is a revision for all of you, right? Because we have done this in 210. So you can represent this typically using an array representation. So in an arrays, what you would do is you'd essentially go in the following manner. You'd have the first element in array 1. So it starts from 1, not 0. Okay. And then the second, the left child will be numbered, will be in array location 2, and then 3, and then 4, 5, 6. This is how you're simply going. All right. And that's how you're filling out your array. And essentially, the size of the array is simply the number of nodes. And there are not going to be any empty holes inside your array. Okay. And so this is an array representation. You can just see that, for example, 16 has 2 children, 14 and 10. Okay. These are the arrows representation. And then 10 has children which are, 9 and 3, and so on. Okay. But it's not necessarily sorted. So you can see that if you go forward in this direction, you have 2 and followed by 4. So it's not sorted. Okay. It has certain properties, but essentially it's unsorted. Okay. Which is what was pointed out over here, that the contents are not sorted. Right. That's what a heap is. It's partially sorted. So now let's see how many of you remember this. If we want to figure out, if you have an index I and you want to find out its parent, what would be the index of its parent? Somebody else? Yes. Yeah, so it's a 4 of I open 2. So for example, if you're looking at the parent of 2 or the parent of 3, you'd simply divide it by 2 and take the floor, that becomes 1. All right. What about the left child? How would you get the left child? Sorry? 2i plus 1. So 16. So 1, go to 2. So you don't think about the right child, right? 2i plus 1. So the left child is simply 2i. Yeah. So, so to be able to get to the parent, you simply take the floor of I upon 2. If you want to get the left child, it's 2i. If you want to get the right child, it's 2i plus 1. Okay. So hopefully all just a reminder. Now, let's take a look at a few procedures. And the first procedure that we're going to look at is max heapify. Okay. So why is it called max? Simply because we're looking at max heaps. We could have defined min heaps, but we'll start off with max heaps. Min heaps would simply differ from a max heap in the sense that the smallest number would be at the top. Okay, so instead of having bigger, you would have smaller than or equal to in a min heap. Okay, so let's take a look at the max heapify procedure. And the idea is that it maintains the max heap property. And the property is that both your children should be smaller than or equal to you. Okay, so can somebody remind me how would I go about, what would be the algorithm to run max CP5, for example, on a node number 2? Okay, so it should again be a reminder, should be something from people who took Comp 210 recently. Yeah. And which one would you replace it with? 14, the larger of the two. Yeah. So you compare, you look at the two children, and if these, if any one of them are bigger, if both of them are bigger, you pick the larger one. Okay, and you replace it with 14, and then you would simply go downwards. Okay, bubble down or float down. Okay. And essentially, that's what this particular algorithm is doing. Is it's saying that, well, you assign L to be the left child, okay, the index of the left child, R to be the index of the right child. And then you also have this condition if L is less than equal to the size of the heap. Why do you think we have this particular condition and this particular condition? So your idea was right, but now we need to implement it. And so we have certain conditions. And any thoughts on yes? Yeah. Exactly. Because the heap size, if you're looking at the array itself is equal to the heap size, the size of heap. Okay. So for example, if you were looking at 9, then the left child of 9 would be what? 18, right? And the size of this array is going to be 10. Okay. So because 18 is greater than 10, it implies that that it doesn't have any children. So that's a nice thing about converting into an array, is that you don't, instead of looking at the actual pointers and figuring out whether the left pointers are null and the right pointers are null, all you need to do is figure out whether the size of the array is, how does the size of the array compare to its left child index or the right child index. Okay, so you simply compare L with the size of the array, and if it is less than, it implies that the left child exists. Okay. And if you're comparing with the right child, it means that the right child exists. Okay, that's sort of like checking whether the pointer is null or not. And then you say, well, if the left child exists and the left child is greater than itself, okay, then we make the largest equal to the index of the left child. Otherwise, the largest is equal to the index of itself, the node that we're looking at. Okay. And we follow the same procedure repeatedly for checking the right. And then over here, we're simply comparing it with the largest. All right. So essentially, that's one way of figuring out which one is the largest number. All right. Yourself or one of your two children. And if you find that the largest is not equal to yourself, you simply exchange it. Okay. That's what we did over here. So we've taken 4 and you replaced it over here. And 14 goes up. That's the exchange. And then you apply it in a recursive way. So you apply max CP5 on the largest. So now 4 is over here, and you're going to apply max CP5 on this. And so it's going to look at its two children. 8 is, what just happened? Okay, so 8 is, 2 versus 8, and clearly 4 is not bigger than 8. So 4 goes down here, and you can see that the recursive procedure works. Okay. Y(n)(1), not x(1)(8) plus x(1)(2). I think I answered that already. Okay. Right. So let's go forward. This is the max CP5 procedure. All right. And again, this should not be something too new. We do have a couple of minutes left, and let's just take a real quick look at the following procedure, which says I'm going to build a max heap from an unordered input array. Okay, so we sort of did this as well in 210, I believe. Okay, so how would one build? So let's assume that you have an unordered input array, and now you want to convert that. You're not getting the data one by one, but you have the entire array together. Okay, and now you want to convert that into a max heap. So any thoughts on that? Got a minute to that. How would you convert? How would you convert an entire array into an ordered? Okay, so it's not an ordered, but we want to convert it into a max heap. Okay, so you're looking at this, so you can see that it's clearly not a max heap. You've got 4 over here, these large numbers over here, so it's completely just a bunch of random numbers. Okay, and there's a hint. One of these has been shaded, and that sort of gives you a hint as to where we would start. Okay, but just think about it, and we'll do it in more detail in the next lecture. But just to get started, how would you approach this problem? And the number 16, that sort of gives you a hint as to how one would start. Yes, come on. Okay, so where would you want to start? Would you want to start at the last location of the array? Yeah. Okay. Yeah. So yes, you have the right idea. Essentially, the reason why this is shaded differently is because this is the only one that has a child. Okay. So these guys over here can sort of be neglected, and you can starting with the first node from the bottom, going leftwise, which has a child. Okay, and then you can apply the idea. Okay. So let's stop over here.